All right, we are back for part 3, well, not section 3 of chapter 9 of the textbook, which is part 2 of our lecture notes. So we're finishing that up. This section continues what we've been learning. So let's see, 9.1. I have to go back and review what 9.1 is because we haven't done it yet. I'm actually talking about the future. We did tests about population proportion last class. So now we're going to do tests about population mean. Okay. So it's using the same stuff we've done before, but now we're going to actually do the null hypothesis and everything with means. So you must use the same guidelines for the normal condition from chapter 8, right? You have to check that the distribution, you have to check that it's normal, right? If they say it's normal, you have to check for independence. You have to check if it's random. But remember, if the observation is skewed, you can still use it if n is greater than or equal to 30. That's the central limit theorem. And then if it's less than 30, you just have to check that it's free from skewness and outliers. So let's do all this with this example here. This one says a radio station claims to play an average of 50 minutes of music every hour. So only 10 minutes of commercials, right? However, it seems that every time you turn to the station, there's a commercial playing. To investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music in each hour. So over the 12 hours, like the first hour, there's 44 minutes of music. The second one, there was 49, okay? So it says, check the conditions for carrying out a significance test of the company's claim that it plays an average of 50 minutes per hour. So we're checking the conditions. I think the word random is up here. Yes, random. So random is checked, right? Normal, we have a data set. So we actually need to graph it and see because they didn't tell us it's normal. So since we have a set of data, what you should do is open up your graphing calculator. I realize my camera's not on. Here we go. You should, now I'm in 2 squares. Okay, it'll be a little bit weird, but that's fine because one view, the top view is from my iPad and the bottom one's from my computer, but I can't turn off my iPad one because I'm sharing my screen. But anyways, so what you should do is put that data into a list and graph it. You can see the shape, and you're going to have to do that anyways to perform the test. So go ahead and do that now. I'm not going to do that, but I'm going to just tell you that once you type it all in the list, roughly symmetrical, no outliers. So we can say it's approximately null. But what you should do is pause this video and put all those 12 numbers in the list, okay? Because you're going to need to do that later. And then if it's independent, we need to check that NP is less than 10% of the population. That's what I'm trying to write. Okay, so do we think that we can say, I'm going to write our same thing, safe to assume. Actually, it's not safe to assume. There are more than 120 hours in a week of music, right? We don't have to assume. We're only doing 12 hours. 12 times 10 is 120. There are more than 120 hours in a week. Because we're using a week. All right. So then now we are going to use all of this to get our p-value. So just like we got a p-value yesterday for population proportion, this is this same formula, but we are plugging in different things for our statistics, our parameter, and the standard deviation, because now we're talking about means, right? And you can, even though the key to knowing this is means is average, right? And we're also talking about minutes. Like instead of proportion, this would be like 4 out of the 5 hours had at least 50 minutes of music. We're not doing that. We're talking about actual numbers. So we're going to use this formula to get our test statistic. So let me get the numbers ready so I don't have to pull up my calculator. Okay, so it's going to be T. Rn is 12, so 12 minus 1 is 11, right? X bar. Okay, this is where I'm going to give you this stuff. So if you put these 12 data points in a list, you need the following information, right? So we need to get X bar. You should have gotten 47.9 minutes. And then you get the standard deviation of the sample should be 2.81. Degrees of freedom, we should already know, is 12 minus 1, which is 11. Is there anything else we need? We need N, but we already have it. Oh, and then what does this mean? Right? So that's the thing we're testing, which is that they are claiming there's 50 minutes of music. Okay. So let's actually solve this. X bar is 47.9 minus the mean that we're given, 50, over S sub X is 2.81 over root N, which is root 12. Okay, so what's the number you should get? I think this one says negative 2.59. Right, for your T score, your test statistic. So then we are just going to find what is the probability that T is less than negative 2.59. Because remember what we're doing is we are thinking if they're saying the mean is 50, we're trying to say what's the probability that it's actually less than that, right? What's the probability that it's not 50? So this side. So that's why it's less than. Okay. Using the mean of our sample. So when you put that in your calculator, you should get 0.0126. Okay. So this is where you're going to be using the TCDF actually, because you put all of this stuff in there to find that probability. Okay, so I want you to pause and try to do the same thing here, right? And then I'm going to scroll up and you can see the answers, but pause and try this on your own. So what we found here, just to go up, is that the probability of, what's our question? The probability that we have less than 50 minutes of music, right? Their claim is 0.0126, so about 1.26%. So we're going to now run this again and go through using p-value and all that stuff. This is like part of a problem, okay? So pause, try the next, and then keep going. Okay, now we are going to use the one sample t-test and get our p-value and all of that stuff. So here's the same formula from before, right? And remember, you can test, we have three alternate hypotheses. One is that the mean is greater than the actual mean they've given you. One is that the mean is actually less than the mean that they're stating. And then the other one is just simply that the mean is not equal to the mean that they're stating. So you just have to remember this as images to show you. These make sense, right? I'm finding this area. I'm finding this area. But here, when it's not equal to, you just have to remember that it's a double-sided test because you have to account for this area and this area, right? It's not in that. It's not equal to, so it could be either to the left or the right. It's supposed to be a star. Okay. Remember, you can only do the one sample t-test if the population is normal or the sample is greater than 30, and then that the population is at least 10 times as large as the sample. So let's run through all this again with a new example. You might want to pause it and type these data points in your calculator so you can run the same calculations, right? This says every road has one at some point, a construction zone which has a much lower speed limit. To see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed in miles per hour of a random sample of 10 drivers in a 25 mile per hour construction zone. So in the States, they'll actually, when there's a construction zone, they will put a new posted speed. So it might be like 45 miles an hour, but then now there's construction, so you have to go, in this case, 25. So you have to slow down. And someone will stand there with like a radar gun and catch your speed. So there's 10 different drivers. This is how fast they were going when they were supposed to be going 25 miles per hour. So they want us to know, or they want us to answer, can we conclude that the average speed of drivers in this construction zone is greater than the posted 25 mile per hour speed limit? And this is just telling you what you should do in your calculator, but we'll do that in a second, okay? So first, let's write our test down and check all of our conditions, right? So what is our null hypothesis? Our null hypothesis is that the average speed is 25 miles per hour, right? The posted speed. And then our alternate hypothesis, they said is greater than the posted speed. So we're testing, is mu actually greater than 25 miles per hour? Okay. And then let's just put a note. Mu equals average speed of drivers in construction zone. So you need to write this on your FRQs and your AP exam. You need to explain what your variable means. And then we're also going to state that we are going to use an alpha of 0.05 because they didn't tell us what to use. So we're going to use that one. All right, so now let's go over here. Step 2, what test are we doing? We are going to do a one sample t-test. Why? Because we only have one sample of data and we don't know the standard deviation of the population. So it's a one sample t-test. I'll write it like that. It always looks like different. For means. Okay. And then now that we know we're going to do that test, we have to check conditions. So we need to check that it's random, which it says up there. We need to check that it's normal. So in this case, you have all of the data. So you need to plot it and check that it's free of skewness because the sample is less than 30. So plot, you need to plot it. That's why I'm putting it here. And then I'm just going to tell you that you can say data is not skewed and free of outliers. So we can say it's approximately normal. Then we need to check the 10% condition. So safe to assume, I'm gonna do this. There are more than 100, are we saying cars or drivers? Drivers. Right, so we only sampled 10. We're assuming more than 100 cars or drivers are going past that area. And now we're actually gonna do the test. We get a different color here. Let's do it in black. So you need to put all that stuff in the list and then you need to call out the variables you need. So when you put all that stuff in the list and do your stat calculations, right? 1 bar stat, you're going to get X bar is 28.8 miles per hour. You're going to get the standard deviation is 3.9. We already know N is 10. So we know our degrees of freedom is 10 minus 1 is 9, right? So I'm putting all that stuff there because it's going to be needed to use the formula. But then at this point, you can choose not to use the formula. You can actually put it in your calculator. So this is where you can use this. You need to go to your stat tests. And then, so you do like, go to menu, go to stat tests, and then click the t-test, right? The one sample t-test. And when you go to the one sample t-test, it is going to ask you to put this stuff in. You need all of this stuff. Plus, it will also ask you for mu sub naught, which you need to know is 25, right? That's the thing from above that they've told us. And you'll also have to put in your, which test we're doing, right? Are we doing mu is greater than mu naught, mu is less than mu naught, or mu is not equal to mu naught? So for this one, we are doing that mu is greater so that the actual is greater than the posted. Yeah, so that we're doing this one. So are people actually going faster than 25 miles per hour? So you need to select that test. And then when you put that in there, right, you're going to get a number out. And I'm just going to tell you what it is here. So hopefully it matches because I didn't put it in mine. But the probability that, let's do this, that, what am I on right? Mu is greater than 25 is 0.0069. That's what I got. I didn't type it in. That's what the solution says. So hopefully it's right. I'll check it afterwards and we'll come back and fix it if it's not. Okay, so now we have this, right? Another thing you can do, so I'm just going to write this here. You can also, if you want from this point, you can find your test statistic, right? You can do this. 28.8 minus 25 over, what is it? 3.9 divided by root 10, and you get 3.05. So you would get the same thing, right? The probability that T is greater than 3.05 is going to be the same thing. So you could have written it either way. You can always find the test statistic and then type that in using your T-CDF, or you can use the T-interval test where you don't need that. Okay, but you should get the same number. And then now we need to compare. So let's go back and put that in green. All right, so our p-value was 0.05. So if I look at it, our probability, our p-value is less than 0.05 because it's 0.06. This one's kind of sloppy, 0.069, okay? So let's say since our p-value 0.069 is less than alpha, now you want you to think, are we rejecting or not rejecting the whole null hypothesis, right? We reject HO. We're rejecting the null hypothesis because it's below the threshold that we've said we're going to compare it against. And we conclude, I'm not going to say we, because they're writing this from I, right? Actually, let's not even write right. I'm just trying to think how, therefore it can be concluded. Let's do that. Something I might see. That there is convincing, sorry, I'm gonna sneeze. That there is convincing evidence that the average speed or mean speed, right, is greater than 25 miles per hour. Okay, so because our p-value was less than alpha, we are rejecting the null hypothesis. And then I think there was something, no, it's part B. So we've done that part. Now part B is saying, given my conclusion in part A, which kind of mistake did I make, type 1 or type 2? So if you don't remember, go back and look at your notes. What's a type 1 error and what's a type 2 error? And then hopefully after you take a look at that, you will say it's a type 1 error. And why? Because we rejected HO. So if you don't remember the type 1, type 2 errors, make sure you go back and look at that. And then we're going to say we could have concluded the speed of the drivers is greater than 25 miles per hour when it actually is not. Okay, look at all this writing. This could totally be an FRQ you see on the AP exam. We're getting to the point where we know enough that these things are going to show up. Okay, all right, let's keep it moving. We're going to do another example, but this time it is a two-sided test. And so hopefully you're thinking about, oh yeah, I know what that means now. All right, so this one's about pineapples. It says, at the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder how this change will affect the mean weight of the future pineapples grown in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crops. The computer output below summarizes the data. So we're trying to see if the irrigation system has had an impact on the weight of the pineapples, right? And I saw the word random here. I saw the word mean, so I know I'm doing sample mean, and we've got all the data here. So this one's different because we don't have a list of all the data. What we've got are the statistics. I said the wrong word, right? So they've already done all those calculations for us. So first is to determine if there are any outliers. Oh, so this is going all the way back to, I can't even remember if it's unit 1 or 2. Remember, to find outliers, you have to do 1.5 times the IQR. So the first step, I'll lay this flat again. I'm going to be looking down, sorry, is to find the IQR. Hopefully you remember IQR is Q3 minus Q1. When I look up here, Q3 is 34.115. Q1 is 29.990, right? These two. When you subtract them, I'm going to give it to you. You get 4.125. Okay. And then we have to do 1.5 times the IQR. So you do 1.5 times 4.125, and you get 6.1875, right? And then remember, you have to add that to Q3 and take it away from Q1 to find your outlier band. So I'm just going to do that over here. When you do Q3 plus 6.1875, you get 40.30. Let's go 3 digits, 2. And then when you do Q1 minus 6.1875, you get 23.802. So if we have any points that are less than 23.802 or more than 40.302, they are outliers. And then we look here, let's see, what's our min? Our min is 26, so that means it's okay because you can't be below 23.82 if the minimum is 26.49. And the max of our data set is 35.47, which is within this bound too. So there are no outliers because our mins and our maxes are within that range. Okay, so all the stuff coming back together. Part B. Do these data suggest that the mean weight of pineapples produced in the field has changed this year? Give appropriate statistical evidence to support your answer. So this is where they want you to run all the stat tests, and you just need to go through those 4 steps and do everything. Okay, I think I have enough space. And then can we conclude? Okay, so that's separate. All right, let's do all this. First, we need to list our test parameter things, right? So what is our null hypothesis? Our null hypothesis is that, did they tell us up here? That 31 ounces, that a pineapple weighs 31 ounces. So that the mean is 31 ounces. And then what's our alternate hypothesis? If we come back up here, managers wonder how this change will affect the mean of the future pineapples grown in the field. So they're just saying they want to see if it changes. They don't want to see if it's more or less. They want to see if it changes. So we are testing that it's just not 31 anymore. And then remember, you need to say what mean is. So the mu stands for the average weight of a pineapple. Does it say like a field or something? Grown in the company's field, right? Grown by the company. Just write it like that. They were going to use an alpha of 0.05 because they didn't give us another one. All right, now we need to check our conditions. Well, we need to name our test and check our conditions, right? So what are we doing? We are doing a 2-sided test. So remember up here, we wrote we are doing a 1 sample t-test for mu. We're doing the same thing, but it's going to be 2-sided, right? So 1 sample t-test for mu, but we know it's 2-sided. Okay, and you might be like, wait, what are you talking about? Remember this picture? Where is our picture? Because we are doing this one, right? This one here, mu not equal to mu naught, it's double-sided. So whatever area we find, we have to double it because we need to account for both sides, right? Because it's simply not equal to. We're not worried about less than or more than. We actually want both. That's why we're doubling it. So then let's just take all of the statistics we need from up there. What do we need? We need, oh, let's check our conditions first. So I already underlined that it's random. So let's check conditions. Random. Check. Okay. Normal. This one's easy because I think we have more than 30. 50. Okay. So since the sample n equals 50, which is greater than or 30. So by CLT, we can do a normal, approximately normal, right? And then we need to check for 10%. So we have, how many do we have again? How many pineapples? 50. So it's safe to assume more than 500 pineapples. You could also say 50 pineapples. I think I'm spelling pineapples wrong. Pineapples is less than 10% of the population. You could say it that way, okay? Let me fix this. This pineapples looks crazy. Pineapples. Okay, check, check. We've checked our conditions. All right, now we need certain things from above. We need X bar. Do they give us the mean? Yes, right here, 31.93935. We need the standard deviation, which is here, the same as on this paper, yeah, 2.394. And we need this, right, which is 31. Okay, I'm going to show you how to do the calculation, and then you can try to verify it with your calculator and doing a test. So remember, you can always find, so I think we've started step 3 here. We are doing the test, okay? The do section. I just forgot to label it. So if you are doing T, remember it's this formula. I'll write it again. It's a minus over S of X over root N. So for us, it's going to be 31.935 minus 31 over 2.394 over root 50. Sorry, I almost did N minus 1. Which I've forgotten to write. So actually, let's write it here. Degrees of freedom is 50 minus 1, which is 49. We need that too, because it's a t-test. Okay, when you work all this out, you actually get a t-value. What is it? 2.762. Okay, I'm going to show you this drawing over here, and then we'll come back. So what we've done is we found out that based on our data, we're looking at things that are 2.762 above and below. Standard deviations above and below the mean, right? Because this would be our mean. So when we find the probability of being greater than 2.762, it's going to be the same as if you said, what's the probability of being less than negative 2.762? So if you're using the t-score, what you can actually do is you would say, what's the probability of the t-score being greater than 2.762? And you end up getting 0.004. So now I found this, I'm going to make it a different color. I found this yellow area now, okay? But I also need to add the pink area to it. So it's going to be the same. So what I can actually do is just double it. And you get 0.008. That's your p-value. So I did all this by hand, but you can also do this in the calculator. So if you want to pause and do the t-test under stats test, and then you just would pick mu not equal, like HO not equal to HA, it should do the double calculation for you. You don't have to account for it, okay? So I would pause and do that and see if you get the same thing, okay? So we found it's 0.08, which is less than alpha of 0.05. So now I'm just going to come over here and I'm going to write my conclusion in black because I'm out of space over there. So I'm going to say, since our p-value 0.008 is less than alpha, which we use 0.05, we reject H naught and conclude, or you could say it is safe to reject the null hypothesis and conclude the mean weight of pineapples, you could say in the company's field or in this year's crop, something like that, in this year's crops is not 31 ounces, right? We just were checking that it's not 31 ounces. So because we've gone over the threshold of 0.05, sorry, because we've not gone over the threshold, I'm going to say that because our p-value was less than the threshold, we reject H naught and conclude that the mean weight of the pineapples in this year's crop is not 31 ounces, right? And then part C is making us think about is it unit 3, unit 4? I think it's unit 3. Can we conclude that the new irrigation system caused a change in the mean weight of pineapples? And hopefully you're thinking, what is the only way to prove a cause and effect relationship? Is that if you've done an experiment, right? And that's what you're going to say here. No, this was not an experiment. That's the only way you can conduct a cause and effect relationship. Okay. And I think we're done. Yes. Okay, we're done. All right, I'm going to stop recording. See you guys next time.